Last week you did some basic ER diagramming, and this week we're going to go into more depth so that you can build an even better data model. But the first thing I want to point out for this week is the term iterate. So developing an ER diagram is an iterative process. I would start with just two entities that I know are related and decide what type of relationship that they are in. Again, one-to-one, one-to-many, many-to-many. Okay, you got those two entities locked in, then grab the next entity. So you're really going through your business rules, deciding what your main entities are and the relationships based on those business rules, and you're continually refining, adding more entities until you have a completed ER diagram. Let's review those types of binary relationships one more time. Now, the term binary relationship simply means binary means two, the relationship between two entities, which is the most common. But you will see in this chapter there are other types of relationships. There's a unary relationship and a ternary relationship. We'll get to that. What I want you to see is I have a man entity and a woman entity. And the same two entities can actually have each type of relationship, one-to-one, one-to-many, and many-to-many, depending on how you're describing the relationship. Let's start with marries. A man marries a woman. So if you think about it in a monogamous society, if you take one man out of the man table, one record, how many related records can this man be married to in the woman? And you know it's one. Then what you're going to do is go in the reverse direction. If I take one woman, how many related records in the man table can that woman be married to? One. So this is a one-to-one relationship. By the way, one-to-one is not very common. It can happen. Your most common type of relationship is one-to-many. So let's take a look at an example of that. I have the relationship. Notice it's no longer marries, but is fathered to. And let's take one man and let's take the woman entity. How many related records, how many related daughters, let's say, can that man have? And it can be many. So really all you're caring is it just one or is it many? I know there can be zero, and we'll get to that later. So at this point, we're thinking, is it one or is it many? Now, let's go the other way around. Let's take a daughter, and how many biological fathers could that daughter have? And it's one. So the relationship is father to between man and woman is one to many. Notice it's the same two entities, but we're defining a different relationships. So that's interesting when you're developing your data model. It could be that there are more than one type of relationship between two entities, depending on how you define it. Let's look at this third example is sibling to. One man can have many sisters and one woman can have many brothers. So in this case, we have a many-to-many relationship. So I hope that helps you in deciding how to define your binary relationships. After mastering the ability to determine the type of relationship there is between two entities, you also want to consider minimum cardinality. Minimum cardinality is either going to be 0 or 1. What minimum cardinality is really deciding is whether you're going to require the foreign key. More on that later. Again, we have a man entity and a woman entity, and our relationship is father to. What is the minimum cardinality of man is father to woman? Does a man have to have a daughter? So that minimum cardinality is 0. And you will see in the Chen model, we're going to just put an O right here along the line of the relationship. And in the crow's feet model, we're going to put an O here too. Now, we still have our types of relationship, which is one to many, and there's my crow's feet in the crow's feet version. Okay, let's go the other way. What's the minimum cardinality? Does a woman have to have a father? Yes. So you notice we have this line through here, meaning that's required. A woman has to have a father. And we have the two lines here. The inside line is the one to the crow's feet many, and the outside line is the required, the minimum cardinality. So that will complete everything you need to do in deciding on the binary relationship between two entities. This is a handy reference for the crow's foot symbols. This means you have to have at least one. This is the one side in the one-to-one or one-to-many. This is mandatory, required. Here we have many and mandatory. Many, mandatory. Here we have one and optional. Here we have many and optional. So the one-to-many part is always on the inside adjacent to the rectangle that represents the entity. And then the optionality, whether or not it's required, is on the other side of that line. You can get even more specific with cardinalities, and you could consider an exact number for minimum and maximum cardinality. And in the Tiny College database, for example, there is a table called Enroll. A student enrolls in a course. And does a student have to be enrolled in a course? No. As you see here, there's going to be a limit of 6 courses that a student can enroll in. Now that is for a semester. I don't know if I agree with this design, but this is the design explaining this minimum and maximum cardinality. A student does not have to enroll, but it can enroll in the max of 6. This does not allow for a dean to make exceptions to the database, and that would be something you would have to consider when you're designing the database. If there is a concrete number for maximum or minimum cardinality, such as a student has to enroll for a minimum of 2 and a maximum of 6, there's no direct way to implement that in the database. In your database implementation, you can indicate that a field is required or optional, but you can indicate the student has to have at least 2 courses. All that is done programmatically with triggers. In this case, course entity, how many students can be enrolled in the course, not how many courses can a student take, but how many students can be enrolled in a course. So a course can exist before anybody's enrolled, but I'm not going to let any more than 35 enroll. How do you implement that in your ER diagram? Student enroll, we have the cardinalities here, 0 and 6. So adjacent to the entity, you're going to put a pair of parentheses with your minimum and maximum cardinality. That is not always done, but when you are designing, if the business rules show you that there needs to be a maximum number or a minimum number, you're going to indicate that here. Now we're going to introduce the concept of strong and weak entities, but before we get there, I have to introduce a few terms. These terms are existence dependent and existence independent. An entity is one or the other. An existence dependent entity can exist in a database only when it is associated with another related entity occurrence. What this means is you have that primary foreign key relationship between two entities, and you've identified that, and then you go back and say, well, what's the minimum number of related records on, and you decide 1. There has to be a related primary key record. Let's look at an example. Here we have the entities employee and dependent, and it's a one-to-many relationship. And let's say the reason for the dependent table is that dependent has the employee's health insurance benefits. An employee can have many dependents, but maybe there's no dependents. But if we take one dependent, can that dependent exist if there's not an employee? And the answer is no. I'm not going to add someone to this table if their parent or whatever is not employed here. So notice that the minimum, this is a mandatory, it's not optional. So employee number comes over here as a foreign key, and it is not optional. So dependent is a existence dependent on employee. Few more terms. Existence independent. So if we have an entity and that is not the case, then it is existence independent. And we will refer to that as a strong entity. And most entities are strong entities. So the other way is usually the exception. Before we can completely identify a weak entity, we're going to identify two types of weak relationships. So weak relationships means it's existence dependent. Strong, existence independent. We have a weak non-identifying relationship. That means that the primary key in the entity that's existence dependent is not a composite key using the primary key from the related table. Oh boy, let's explain some of that. Here we have course and class. I want you to think about this. A college is offering a class, and there are a list of courses that the college can offer. It is not possible for the college to offer a class if the course doesn't exist. Like the college is not going to offer a class at 5 o'clock and, well, we don't know what we're going to be teaching, for example. No, I need to know what course it is. Here we have course, and the primary key is course code. It comes over here as a foreign key. And the primary key in class is class code. Now, course code has to have data in it, but notice it is not part of the primary key. So we're saying that's non-identifying since that is not part of the primary key. And we just generate a number like at HCC, 13366. We just generate a random number. We call it class code. It does not have to be like that, because here we have the exact same relationship, and let's say a random number is not just generated. You notice that course code now is here as part of the composite primary key. Accounting 101, Section 1. Accounting 101, Section 2. So putting down the course code and the section code together uniquely identifies each class being offered. This is an identifying. I call this ID dependent. I don't call that a strong relationship. I call this ID dependent because I have the primary key ID here as part of the composite primary key in the class table. So looking at this ER diagram, it looks pretty much like a regular ER diagram, but I'm going to identify this as a weak relationship because of this line right here. That means it must have a related record. Class is dependent on course. I note over here that the foreign key is not part of the composite primary key. So this is a weak non-identifying relationship. I look at this example here, I can tell because of this that this is a weak relationship. And now the primary key is up here, as well as being part of the composite primary key. It's also the foreign key. So this is a weak ID dependent or identifying relationship. Now we can define weak entities. So a weak entity is existence dependent, and it must have a primary key that is partially or totally derived from the parent entity in the relationship. That means this is a weak entity. This is not a weak entity. Lots of stuff to confuse you here. This is a weak relationship. This is not a weak entity. This is a weak relationship and a weak entity. The weak entity is the combination of the two. Let's move on to look at attributes in our ER diagram. There are 7 characteristics discussed in the chapter. Let's start with the first 2. Is an attribute required? Must it have data in the field, or is it optional? You need to think about this when you're designing the database and indicate that in your data model. Then when you are implementing the data model into the actual DBMS, you will know that a field is required and you will indicate that as you're creating the SQL for that. There is no way to indicate that an attribute is required or optional in the Chen method, but in Crow's Feet, you will bold those attributes. Here we have a student, and student last name and student first name are required. I believe this is a typo in the textbook. Student initial is not going to be required, but I'm not going to create a student record unless I have their last name and their first name, and that bold is indicating required. Attributes have a domain. That is the set of possible values for a given attribute. Here is an ER diagram of a student entity, and you will see that the social security number and the L name are in bubbles. So that's how you indicate attributes with the Chen notation. You will see a domain indicated outside of that bubble for social security numbers. So social security numbers has the domain of digit, 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 dash, digit, digit, dash, digit, 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 digit. This goes back to the old COBOL days when 9 indicated that 9 was a placeholder for a digit. Notice also that there's an underline under the SSN attribute, and that indicates that the SSN is going to be the required field in the student entity. Here is another ER diagram adding the state field to student and indicating a domain of 2 characters. But that just simply is not enough because and YY. I would be allowed to enter YY, that's 2 characters, but that is not a state. So one thing that database designers will do to make sure that our data is correct is create lookup tables. And those lookup tables will look up the proper state code, for example, and make sure that only data in the lookup table will be allowed into that field that's doing the lookup. So to create a domain of legitimate values for state, you're going to add another entity. So here I've added a state lookup table to this Chen diagram. I had previously indicated a domain of just 2 characters. There would not be enough data integrity because, as I mentioned, you could have YY as a state. Now I have a state lookup, and I will only indicate the 50 states as records in this table. So, for example, FL will be in there, DE, CA for California. Those values will be in here. And I'm indicating that's a primary key in the lookup table, LKP for lookup. Student lives in this state. State now is italicized here, and that means it's a foreign key. And I don't know if you recall the concept of referential integrity. It was introduced in the last chapter. Let's review that, and you'll see why doing this will help us keep our data clean. Page 75 of the text defines referential integrity as a condition by which a dependent table's foreign key must either be null or it must have a matching entry. Let's think about this. Here I have a product table with a vendor code as a foreign key to the vendor table. Let's say I add a new product and put 999 down for the vendor. As you see, there is not a 999 vendor code. This is the primary key in vendor, and there's not a 999 here. Referential integrity is going to say, no, you cannot add 999 here. You can keep it null, or you can add any of these, but you can't add something as the value in the foreign key that isn't related, doesn't have a related record in the primary key. Now, YY in state, that's not in the table, so it's not going to accept that as a state for a student. As you're adding your fields, you may identify candidate keys or fields that are unique, And you want to indicate what those are in your design, because how you write your SQL to create your tables will depend on the fact that you've identified those fields as being unique. In the ER diagram, you can have one or more fields also to be your primary key. And in the Chen model you just saw, you will underline that. Let's take a look at this. Professor has a PK, notice it's underlined. And then we also have some fields that are in bold. So these are required fields in Professor. Another group of characteristics for attributes are whether the attributes are single valued or multiple valued. This is different than composite versus simple. Composite versus simple attributes means that the attributes are atomic. Single valued means that the attributes hold one thing, still simple, or multi-valued attributes means it can hold multiple groups of the same thing. Let's take, for instance, you decide to have a student table, and in the student table, you add courses that the student has taken. Since the student could take 5, 15, 30 courses, course in the student table would be multi-valued, and that would be an error. So wherever you identify multi-valued attributes in a table, know that you need to pull that out into a new entity. Here is an example from the textbook. We have here in the text on page 117 ER diagrams using Chen model and Crowsfoot model. And it's decided that a car can have a color as an attribute, but then on consideration, a car can have more than one color. Maybe, what's color mean? The interior color, the top color, the body color. So you can see in the Chen model, you identify multi-valued attributes using a double line. Crowsfoot model, hard to identify that. The solution is that's got to become another table with primary key here and another field identifying whether it's the interior of that car or the top of that car. For example, on page 118, the author says, though you can have a conceptual model with an M-to-N relationships and multi-valued attributes, you cannot implement it in a relational database. So you need to decide, am I going to break up the multiple values within this table, not add a new table? Now, there may be reasons to do that, because when you're querying, you will not have to join tables, which does slow up the results. But how many extra fields do you add when you do this? This might work, actually, if you only have in a car a top color, a trim color, and a body color. This will work. But if the car designers decide now to have a dashboard color, for example, you see you would need to add an extra field. And how far does that go? So that is one solution, and it could work if you don't think there's going to be a lot of extra modifications. But let's talk about this again with student. If a student, let's say, oh, well, I'll just have a course 1 and a course 2 and a course 3. How many course fields are you going to add for a student? What if you say, well, 20, I'm going to add course 1 through 20, and a student takes a 21st course? There's nowhere to store that data. So in that example, course does have to go, the courses that a student has taken does have to go into its own table, because you can add as many rows as you need to, as long as each row is unique in that table for courses taken. One other thing, if you did decide to add 20 course fields to student, I'd say that's never going to be exceeded. No student is ever allowed to take more than 20 courses. If the average student takes 2 courses, you have a lot of null data. Every student record on the average would have course 3 through course 20 null. And that is not a good database design either. Remember, we're trying to minimize the null fields. Here I have created the initial table, and initially car color was all one field. And how do you implement that? Well, in this one, I just made it a comma-separated list. I don't know if red is the interior or if red is the exterior, but the car does have, car ID 1 does have red, white, and blue. And car ID 3, blue and black. Or in this case, I said, well, let's do pipes, these little lines to separate each one. So you got to decide, if you're going to do it like this, what's separating each value. Here's the problem. Suppose I want to query every car that has a blue color. And if, as a human, I'm looking at that, and I agree this one and this one both have blue colors. But unless I get very specific in the query, the only record that's going to show up is this one, because when the query just looks without me getting very specific and writing functions and code, it's going to see this as red, white, and blue. Red, comma, white, comma, blue does not equal blue. So that color would not show up in a query. But if you did break it up into multiple tables, blue would be by itself in one of the color codes. So here is a very good solution then. We have our car. Notice anything to do with color is removed from the car table, and we have a one-to-many relationship. A car has a car color. And notice we're going to talk about this ID dependent type of entities later, but the primary key from here comes over here as a composite primary key. So I'm looking at car number 1 and I'm looking at a section. This is part of the composite key. And let's say I can have that the top of car 1 is white, or the trim of car 1 is gold. So I can indicate different sections. Let's say a dashboard becomes a new section. That's not a problem. I probably will create a lookup table called section. All I have to do then is add a new record with a value of dashboard in section, and that will allow section to be here. So this is a very good way to solve the problem of multi-valued fields. Another thing to consider when you are deciding what attributes to add to your entity is derived attributes. When I first became a full-time database administrator, the lady that had the position before me had a new module to add called Next Generation. And these were the children of the owners of these places. And she decided we needed to know the age. These were adult children that probably will become the owners eventually. She added an age field. When I looked at that, I decided, how do I know right now what the age of the person is? If that data was entered 3 years ago, let's say the age was 40. Is it 43 now? Or how do I know this age wasn't modified last month? Age is a derived field. I would not create ever a field called age in a database. I volunteered and created a database for the Senior Olympics in the mid-90s, and we had to know the age of the participants because each event was broken into age groups, so 50 to 55, 55 to 60. So we didn't have an 80-year-old competing against a 55-year-old. We always had repeat participants from year to year to year, and I had to calculate the age and put them into the right group. I didn't store age, I stored birth date. And from that, you can apply functions. And every year I decided what age group through functions based on the birthday. When you create atomic attributes, you can always get back to the composite attributes using functions, using string concatenation. So if I have a first name field, a middle initial field, and a last name field, I can very easily in a query make it seem like just a name field. So keep attributes atomic. Usually don't store calculated data. There is an exception, and that is with general ledgers and accounting. Because of auditing and tax purposes, even if an invoice total is calculated, I would still store that data. So a derived attribute, you don't store it directly, you derived it using a function or an algorithm. Table 4.2 in the text lists some of the advantages and disadvantages of storing derived attributes. So the advantage, again, if you decide to store it, is you're not going to run that function on every record, and it's going to save you some time when you're accessing data. However, with how fast CPU cycles are now, I don't know if that's a big concern unless you're dealing with a lot of data. If you decide not to store it, you're saving storage space, and you're always getting the latest value. Again, with age, am I computing the correct result? Is that data for the derived attribute stale? The disadvantage of storing then the derived attribute is you gotta always make sure you're updating that piece of data. If you don't store it, the disadvantage is you gotta process it. Well, these kind of are the opposite here. I still would go usually with not storing the derived attributes. Last thing we're going to discuss in this lecture is relationship degree. So far, we've only looked at a binary relationship. We've looked at two entities, decided how they are related to each other. Let's define what unary, ternary, and recursive relationships are. Here is the unary relationship. And notice that the line is drawn from employee to an employee, and the relationship condition is manages. So an employee record manages another employee in that same table. Or take an employee, that employee is managed by another employee in that same table. Notice there's a one-to-many relationship, and there might be employees that don't manage anyone, and there might be employees that don't have a manager, the boss, for example. Here's our binary relationship, which we've been doing, and here's a ternary relationship. So a doctor and a patient and a drug is only prescribed when a doctor prescribes a particular drug to the patient. And this is shown as the conceptual, but logically, we're going to, because this is many to many and many to many, and we can't directly implement many to many, logically then we're going to add a composite entity or a junction table and convert the many to many to one to manys, and that is the prescription. So a doctor writes a prescription, patient receives a prescription, and a drug appears in the prescription. So I have a list of all drugs, amlodipine or etc. I've been taking care of mom, so I know some of the drug names. A unary relationship might also be called a recursive relationship. Relationships can exist between occurrences in the same entity sets, like an employee manages an employee, or a product is used to build another product. Those are examples of recursive relationships. In this example of a recursive relationship, let's take a course such as Java 2, and the courses table has Java 1, Java 2, and Java 2 has a prerequisite of Java 1. Java 1 and Java 2 are both courses in here, and they're related to each other. Let's redefine that associative or composite entity. Referred to it in week 3. Whenever you have a many-to-many relationship, you cannot directly implement it. You're going to implement it with a composite entity. So a student can take many classes. A class can have many students. That's a many-to-many. And we're going to remedy that with this enroll table. And I'm going to make another video over this concept. So if you need some reinforcement on what composite entity does, take a look at it.